Hi, everybody. This lecture covers the second part of Chapter 2 in the Electric Circuits textbook. That corresponds to sections 2.2 and 2.3. And this is a very important lecture because some very fundamental and important relationships, mathematical relationships that govern electric circuits are addressed in this section. So let's start at the beginning, part 2 of 2. All right, so the first thing is we need to talk about, we've already talked about elements that supply current and elements that supply or that create a voltage drop. And so we were familiar with the variables V measured in volts and the variable I measured in amps. The third big unit and the third big type of a circuit element is a resistor. And a resistance is actually a measure of a capacity of a material to impede the flow of current. I kind of hate that word impede because there's also a quantity called impedance. So we're not really talking about that in the technical term. But when we talk about resistors, we're talking basically about a passive electrical component that limits the flow of electrical current in a circuit, kind of a way. So limits rather than impedes. The property of resistance is modeled by a resistor, and in reality, everything, whether even a copper wire, has some resistance associated with it, although some things have high resistance and they're taken into account. When we're modeling, when we're creating, what would you say, ideal or simplified circuits, we don't include resistance from elements that have very, very little resistance. But basically, this symbol, the jaggedy line, the zigzag, is the symbol for resistance. And basically, we have, if you look at this, we have I, which stands for current, and V, which stands for voltage, and R, which stands for the resistor. There are also different appliances and things like a flashlight or a light switch or anything will have a resistance associated with it. But R as resistance is a big part of an electrical circuit. So here we measure voltage in volts, we measure current in amps, and we measure resistance in ohms. And it is assigned the Greek letter omega, capital omega. So the symbol for ohms is the Greek letter omega. Okay, so on a resistor, Ohm's law describes the relationship between voltage and resistors. And Ohm's law is one of the biggest and most widely used laws that governs the relationship between different electrical components. It's used to talk about electricity. So voltage is equal to resistance times current. And because the units are consistent, we have volts is equal to ohms times amp, or any other way that you can structure that relationship. But they are consistent. There's no conversion factor required. So once again, it becomes really important to take everything back to base units. Okay. So what about the sign? Well, isn't that interesting? Okay, so the first thing is that power going through a resistor, which we'll talk about in just a moment, is always positive, meaning you always are absorbing power through a resistor. But here, when we have I flowing from positive to negative voltage going through a resistor, what we want to do is to use that same passive sign convention that we first talked about back in chapter 1. Okay, so here's a little bit of a different way to express it. The reciprocal, 1 over the resistance, is called the conductance. And in the same sense that if you look at this equation, I is equal to plus or minus G times V. Remember, we had V is equal to IR. So what we basically have here is, since G is equal to 1 over R, I is equal to V over R. So it's just another way of writing the same equation, except that conductance, variable G, uses the unit of Siemens and is abbreviated with an S. All of these Siemens, ohm, are named after the last names of some great scientists when all of this was coming about. Okay, so like we talked about, when we talk about the power on a resistor and we set up the equation, we know that power is equal to V times I. And we know that V is equal to R times I. So we have R times I squared. Since resistance is always positive, and I squared is always positive because a negative number multiplied by itself is positive, a positive number multiplied by itself is positive. The power going through a resistor is always going to be positive. That means that the resistor will always absorb power, which makes sense. It's not going to supply power. It's a resistor. It's impeding, to use their term, or restricting or limiting the flow of current in the electrical circuit over that component. Okay, so once again, always power on a resistor, always greater than 0 because of that squared term in terms of the math and in terms of what a resistor does in terms of the function of the circuit. Okay, so here's just another discussion. Oh, even if you use different quantities, guess what? We still end up with positive power through a resistor. Okay, so here we talk a little bit more. This is a very simple circuit that's constructed. We have an independent voltage source, we have a current, and we have a resistor. And it asks you to do some calculations, basically what the power is. Well, the first thing is we can calculate the resistance because it's going to be a voltage divided by I, because remember, voltage is equal to I times R. So when we divide both sides of that equation by I, we get resistance is equal to V over G. We know that V sub G is going to be constant throughout the circuit because there's no other voltage sources. We also know that I is going to be constant because there is no other source for the voltage, or the amperage, excuse me. So we can calculate the resistance, which comes out to be 200,000 ohms or 200 kilo ohms. So the prefixes work exactly the same way as all the other SI quantities. Well, how do we calculate the resistance, the power from the resistance? It's Ri squared. We plug those numbers in. Everything's consistent because we remember to use base units. We are using ohms, not kilo ohms, and we're using amps, not milliamps. And we come up with the resistance of the circuit as being 200 kilo ohms, and the power that is absorbed by the resistor as being 5 watts. All right, here's another simple circuit, independent voltage source, a current, and a resistor. We're given a value of the power, which is negative 3 watts. And we are given a voltage, an amperage of 75 milliamps. We want to find voltage and we want to find resistance. All right, so what do we find first of all? Well, the V is calculated at 4T, which is just a negative power over I based on the first equation. And then after that, we also have I sub G, the current, which is 75 milliamps. When we plug those in base units, we get the resistance is 533.33 ohms. We then use that value and the current in amps, not milliamps, squared to calculate the watt, the wattage or the power, and then we can see that the power of the resistance is the negative of the power associated with the power that's being generated, and it's equal to 3 watts. All right, so we just calculated it to be 3 watts. What does that mean? It's absorbing for two reasons. One is because it's positive, one is because it's a resistor. So we have a mathematical reason, and we have a boots on the ground reason for why it's positive. Okay, suppose we're told the voltage drop across a 50 ohm resistor is 10 volts. What's the power? Okay, well, you can just do that same calculation. Turns out that it is 2 watts, and you don't need to know the voltage polarity because it's always positive, because that's what a resistor does. All right, the next big law that we're going to talk about is Kirchhoff's law, and we're going to talk about two different versions of the law, but they both govern the way that electricity or that charge or that current moves through a circuit. So one of them is based on voltages and one of them is based on current. But they basically say the same things, and they give you a total of 6 equations that you can use to solve electric circuits. This is really important because, as you remember from algebra, that if you have one unknown, you can solve it with one equation. If you have two unknowns, you need two independent equations and so forth. So if you have 6 unknowns, you're going to need 6 equations to solve for that. So the more equations you have that govern the behavior, the more unknowns you can solve for. Okay, so this is just a review of your of a little bit of algebra with a electricity flare. To solve for 3 unknown voltages and 4 unknown currents, how many independent equations do you need? Well, that is 3 unknowns and 4 unknowns, which is 7 unknowns. So the answer is you need 7 equations. We don't have 7 equations at this point in time. It's just asking a general question about how simultaneous linear equations or simultaneous equations, whether they're linear or not, actually work. All right, so Kirchhoff's law. The only equation we know at this point is Ohm's law, V equals IR. Okay, so if we do that, we can look at these resistors and we can calculate a voltage, because if V equals IR, we can take I at going over the first resistor, multiply it by the resistance, and of course it's 2000 because that's kilo ohms. V2 is the same thing, V3 is the same thing. We don't know anything about the relationship between I1, I2, I3, and the supplied current, or the current that goes through the supply. So we don't really know anything about that at this point. So Kirchhoff's law is going to correct that for us. Okay. So if you look at this circuit diagram, and once again, when we're doing circuit analysis, you always want to draw that really clear circuit diagram. We have a 25 volt independent source with a current flowing through it of I sub G. We don't know really what the current is here, but we know we're going to call it I sub 3 because we have V sub 3. We don't know what the current is here because it's I sub, but we call it I sub 2 because this is V sub 2. And last but not least, we have I sub 1 because it's flowing over the first resistor. So V sub 1, I sub 1 go together, and so forth. All right, so what can we do with this based on Kirchhoff's law? Okay, so the first version of Kirchhoff's law is Kirchhoff's current law. It says the algebraic sum of all the currents at any node in a circuit equals 0. So what is a node? A node is a place where any two things come together. So A is a node, B is a node, C is a node, and D is a node. So we have 4 nodes in this particular circuit. Okay, so if we go back to that, pay attention now, since we're talking about I guess I'm skipping ahead, sorry. It just asks how many nodes there are. A, B, C, D equals 4. That is the correct answer. All right, now let's talk about analyzing everything at those 4 nodes, at A, B, C, and D. All right, so what we do is we decide if we're going to look at the current entering or leaving the circuit, or the node. Pardon me for saying that. Okay, the other part of this is we may have too many equations, but that'll come out in the wash. If you just do the math and set it equal to 0 on entering or leaving, then you're going to be just fine. So here at A, we have I sub G plus I sub 1, because those are the two currents that are associated with A. They have to add to 0. At B, we have I sub 1 and I sub 2. And that has to add to 0 as well. I'm going to talk about entering and leaving in just a minute. The way this is drawn here at C, we have I sub 3 and I sub 2, but the equation looks a little different, which I'll explain in just a moment and give you an alternative way to think about it. And then D, we have I sub G and I sub 3. All right, so the way that we think about this is we look at those current arrows and we look at them in relationship to the node. So here at A, is I1 leaving or entering? And the answer is it's leaving because it's pointing away from the node. How about I sub G? Well, at A, it is also leaving because it's moving away from the node. And it's also really important to notice that this happens instantaneously, essentially because electricity travels at the speed of light. But we're talking about drawing the circuit and what's happening with the node. So in other words, here I1 and IG are both leaving. So they're both positive because we look at this as leaving. We could look at it as entering and calling them both negative, but that would kind of be silly, right? How about at B? This one's entering, this one's entering, so let's look at it as entering. I1 plus I2. What about here at C? Well, we have one leaving and one entering. Okay, so we're just saying I2 equals I3. I might think about it as being a negative. So in other words, if I looked at this as leaving the circuit, I would say I2 would be positive, but I3 is entering the circuit. So I might think about that as being a negative leaving. So I could think of entering as being negative leaving. And I would write this as I2 minus I3 equals 0. Okay, then what about at node D? We have IG is entering, I3 is leaving, which is just kind of what we just talked about. So I would talk about that as being IG is going in. So if I think about this as being is leaving, IG would be negative, I3 would be positive because it is in fact even leaving, and it's equal to 0. All right, so if a circuit has 6 nodes, how many independent equations can you write? Well, there's only 5 because you're going to have that redundancy, and that's sort of why they look at this on C as being I2 is equal to I3. There's really no new information there. If you think about the variables, we have IG, I1, I2, and I3, right? There are 4 variables. So this is kind of a redundant equation, or at least it's not fully independent. Okay, so if you have 6 nodes, how many independent Kirchhoff's current law equations can you write? KCL, Kirchhoff's current law. It's 5. One of them is going to be dependent. All right. All right. Now, here's the other version of Kirchhoff's law, which is also very useful. We now have 3 equations, and we have 3 more equations that are independent from Kirchhoff's current law. But we have 3 from Ohm's law, which we've written out over and over and over again. So we know those, and then we have the KCL. Now we have another law that Kirchhoff came up with for voltage. The algebraic sum of all the voltages around any closed path in a circuit equals 0. Now this is really interesting because even if you have something running in parallel to each other, anytime you have a piece of that that's closed, it's still going to sum to 0. A closed path starts at any node, travels through selected circuit elements, not necessarily all of them, and returns back to the starting node. Without including any intermediate nodes more than once. Okay, so the path has to be clean, it has to not cross over itself, but it does not have to be the entire circuit. Okay, and the algebraic sum of all the voltages around any closed path in a circuit equals 0. So you know that voltage is going to be either positive or negative. If current travels from positive to negative, we call that positive using the passive sign convention. If the current travels from the other way, if we take a look at V2, let's just do it this way. Start here at A and go clockwise. I1 travels this way. So let's just do that instead of doing the voltage. So that's going to be positive. Here, I2 is going against my path of travel, so it's negative. Here, I3 goes against my path of travel, so it is also negative. And here, I sub G goes against my path of travel. Those four things are the only places that voltage come from, and they sum to 0. If we were to start somewhere else at D and go counterclockwise, we would have positive, positive, negative on V1 and positive again. So once again, since it's equal to 0, it really doesn't matter if you do it clockwise or counterclockwise, but you have to do one or the other. You can't mix and match. All right, so then for these voltages, we have Ohm's law, and if we have, if we knew the current, or if we wanted to do something about summing the current, we could do that, and we have the resistance. So we probably are going to have enough equations to solve this circuit. All right, so now, as it says, we have 7 equations and 7 unknowns, so we can plug them in. And the analysis of the circuit with resistors and constant sources is based on the use of Ohm's law, Kirchhoff's circuit law, and Kirchhoff's voltage law. However, we will develop some useful analysis techniques that will not require us to use all 7 equations, but we have those 7 at our disposal. And sometimes we can do it with just one equation. All right, here's a good one. How many unknown voltages and currents are in this circuit? Okay, so we know the voltage here. We do not know the voltage here or here. We know the amperage here. All right, so we don't know the voltage. So we have 1, 2, 3 unknown voltages. Can we calculate them? Absolutely, but right now they are unknown. How about currents? We don't know the current here. We don't know the current here. We don't know the current here. But we do know the current here. So we have 1, 2, 3 unknown currents. All right, final slide. How many Ohm's law, Kirchhoff's circuit law, and Kirchhoff's voltage law equations will we need to solve this circuit? Okay, well, you're going to need, you have 6 unknowns, so you're going to need a total of 6 equations. So Ohm's law, V equals IR. We have 2 R's, so probably we're going to want to use 2 of those. Circuit law, we're going to have to use 2 of those. We have 2 branches. And voltage, we also have, excuse me, not branches, 2 closed loops. So here's one closed loop that we know the voltages have to equal 0. And here's another closed loop where we know they have to equal 0 as well. Then we can analyze based on the nodes on those circuits, on those closed loops as well. All right, everybody. So that's it for Ohm's law, KCL, KVL. Those are really heavy hitters when it comes to solving electric circuits and constructing those, thinking about things in terms of those laws can also help you to draw those circuit diagrams to do more advanced analysis. But this is really fundamental to getting those things done. So that is the lecture for sections 2.2 and 2.3. I'll post homework for that. And once again, underneath the submit homework for chapter 2, there's a list of problems to do for 2.1, because that was the first lecture. Then there will be a list of problems to do for 2.2 and 2.3, because that's the second lecture. And then I'll continue, do 3, 4, and 5. Excuse me, 4, 5. I guess that's it, just 4 and 5. So, but when you'll do all the homework sequentially probably, but then you'll keep all that homework from all of those sections in chapter 2 and turn it all in together. All right, thanks. Have a great day.